Hello. Good morning, everyone. Today is October 10th. We start with our business intelligence class. Do you have any questions from last lecture? I recommend you log into the YouTube channel and with a pseudonym, not with your name, so that you can ask questions there. Okay, so maybe the first lecture was not so technical. We start today with the topics, and then it would be interesting to see how it develops. Okay. So the other day we saw a framework. I gave you a framework in which we're going to be navigating, which was a socio-technical system, social and technical, and then we had a third axis, which was the digitalization axis, and in this we had three levels. First was the data, then the knowledge, and then the value. So from data we get knowledge, and from knowledge we create value. Today we are going to look at this first step. After we know what we're talking about, we can continue and try to create some value by understanding the data, which will be our roadmap for the lecture until the end. Okay. We talk about intelligence, but this is more a marketing thing. We don't understand what is intelligence in the human brain, so we cannot replicate it with computers. Okay. We just do some approximation. So data sets can be classified into groups. Data sets can be Euclidean, if a metric can be defined to measure or to describe the distance, and non-Euclidean if no metric or otherwise. Okay, so all other data are non-Euclidean. So examples of data sets that are Euclidean. Basically, almost all the data that you know intuitively are Euclidean. Imagine you have a time series. Okay? What you have when you have a time series is you have the time, and then you measure some metrics that happen in time. It can be the stock exchange, it can be the position of a truck, it can be the value of some, okay, so whatever happens in time is Euclidean. Why? Because you can measure the distance between one time point and one time point. This distance can be measured. In this case, it's just the average T2 minus T1. Okay? That is a distance. So, and this can be measured because time is a constant, is a line that goes and on and on and on. Okay? Also, a picture. This is one-dimensional. Time series is one-dimensional. A picture, let's say black and white, is two-dimensional. What do we have here? We have also an axis X, an axis Y, and we have a bunch of pixels. Let's say I am going to paint now an eye. Okay. We have a bunch of pixels. It's open. And the other day I met a guy, one boy, that had golden eyes. Crazy. He was coming from Armenia. Eyes, the color was gold. Incredible. Crazy. Yeah, so imagine this guy has blue eyes. It's so impressive. And the pixels if we make a picture of his eye, okay? The pixels of this eye are blue. They're all together and they're blue. Okay? What happens here is that we identify this to be an eye because it has a certain shape. But if we zoom into our picture, what we will find is we find a bunch of little tiny pixels. Okay? That are close to each other. These are pixels. These pixels have a position. I can identify the position of the pixel. X1, Y1. Okay? I can identify the position of other pixel. It's like a matrix. I mean, I am doing it very roughly. I hope you understand. And I can measure the distance between the two pixels. So if I translate this without the image, basically what we have is one axis x, one axis y, and then one point x1, y1, one point x2, y2. Okay? And I can measure this distance. This distance can be measured. Easily, okay? So, because pictures are Euclidean datasets, we can use deep learning with them.
Does it have to do with verifications that you need to do? It's like select with or by, so it's like an image and you click the switch.
No, that doesn't have to do with it. It is just the fact that the pixels are organized in this way. Imagine the pixels would not be Euclidean and we would find the blue eye pixels distributed. So you make a picture and then the pixels of the blue eye are not all together to form a circle. They are distributed in the image.
I just thought because there was a way that the companies were using to get data to make a machine.
We are looking here at the structure of the data, okay? So that's the key. And if the pixels wouldn't have this structure and all blue pixels of the eye would be together, we would not recognize the eye. We would recognize some pixels scattered, right? And then we would not be able to apply methods like deep learning to recognize the eye as your eye. And that's why our phone recognizes a face and can be unlocked, because it uses deep learning to recognize the face. We will learn how this works in this lecture, how deep learning works with numbers, okay? But that comes in a couple of weeks. Right now, we're just looking at the data structure, okay? And the fact that we can measure a distance is here relevant, okay? Does it make sense so far? So, also, if you find a picture in color, this is not only 2D, this is 2D times 3, because we have one channel which is channel R, the red channel, the blue channel, and the green channel. So each pixel that you see in reality are 3 overlapped values on 3 different layers. Okay, these values, by the way, take each pixel takes the value between 0 and 255. The reason for this is each pixel has 8 bits. Each positions 1, 2, 3, 4, 5, 6, 7, and 8. And each one of the positions can have the value of 0 or 1. So if you do 0 or 1 are 2 possibilities to the potent of 8, you get 256, So all the combinations of zeros and ones are 256, and that's why you have values between 0 and 255 in the pixel when it's black and white or gray values. Okay, so here you have three possibilities. So for the red channel you have 0 to 255. For the blue channel you have 0 to 255 and for the green channel you have also 0 to 255. Basically, whenever you see a color picture, what you're seeing is a cube of data. Okay, so a cube that has here 3 channels, R, G, and B, and then has the positions X and Y. So when we analyze a picture in color, our data set is a 3D, it's a cube of data. Do you have any questions? No? Good. So this is, if you have a video in color, you have the 3D plus the time, another dimension, maybe the sound can be also another dimension. So at least you have 5D when you have a video, and so on. If you have data of a nose, like how do you say, olfactive, it's usually around 12 dimensions. If you have data from your haptics, like imagine you're programming a robot, you get data from your haptic. So haptic, it's around 6 dimensions, and so on, okay? But the physical world is Euclidean. Whenever you are analyzing something happening in time or happening in the physical world, you will have an Euclidean data set. Okay, so the hypothesis here is that the underlying structure of the data allows for the calculation of a distance. This implies there is a way to measure between points in the space. Okay? But not all data sets are Euclidean. Some are not Euclidean, and they are important. So these are examples of Euclidean data sets. Any questions? questions on the remote side? Those of you online. So the paradigmatic example of non-Euclidean datasets are or is networks. And networks are every fucking where. Think about it. You have a logistics team distributing parcels around a town. You have a network of people moving around. They're moving in the space, but they are a network. Okay? You have a bunch of friends. Some are better friends than others. You have a network there. You have a brain, some neurons communicating to each other, doing weird stuff, making you what you are. That's a network right there. So no networks, no life. Everywhere. All living beings are communicating to each other somehow to all others. Okay? It's called environment, it's called ecosystem, call it whatever you want. Networks all over the place. When you become responsible for processes or for equipment or for servers or for IT stuff, when you become responsible, you are managing networks. So this is a non-Euclidean dataset. And you need to learn how to analyze non-Euclidean datasets with a certain set of tools. Okay, and that's what we learned today. So what is a network? Of course, Facebook, Instagram, TikTok, Twitter, all that stuff is network based, okay? So intuitively, a network is formed by nodes and edges connecting the nodes. Can be directed or not. And some attributes of those nodes and those edges, okay? Some information that can be within these nodes and edges. So, a network is defined mathematically by a set which means a group, okay, of nodes and a set of edges this group of sets is a set of a set is called graph. G. Okay? So a network equals graph equals the union of a set of nodes and a set of edges. Okay? Meaning N are the nodes and E are the edges. So, is that cool?
The nodes would be the points.
Yeah. Yeah, let me give you an example. So this would be the nodes. Say 1, 2, 3, 4, 5, 6. Can be distributed. 1, 2, 3, 4, 5, and 6. And then there is a connection between 1 and 2, 1 and 3, 2 and 3, 3 and 4, 3 and 5, 4 and 5, and 4 and 6. Okay? So, our set of nodes N is 1, 2, 3, 4, and 5, and 6. Okay? Our set of edges is the connection between 1 and 2, the connection between 1 and 3, the connection between 2 and 3, the connection between 3 and 4, 3 and 5, 4 and 5, and 4 and 6. Okay? Yeah.
What would be the attributes in this example?
There's no attribute here, but I could say these are the color is the attribute, being the sex or the weight or the color of a product. I don't know. Okay.
Entirety of this set would be the G, the graph.
What was that?
So the G would represent the entire set.
The G is the union of both sets. So attributes would be blue, and violet, okay? Yeah.
I mean, if you print it on a 2D paper, so if you put a coordinate system on it, you would have dots on a coordinate system.
Yeah, but
but it's just not possible mathematically, or does it make sense?
No, it does not. At this point, does not make sense. If you have, let's say, a distribution of Amazon parcels in a city, okay? If this is a city, you could say this is my network of my trucks, And you can measure a distance between them, yes. But at this point, we're talking just about a network in general. And if you think about Facebook network, there is no distance in there. You can be friends with somebody in Australia, communicate on real time without the same speed as you communicate with somebody in München, right? So there's no space there, yeah.
And at this point, we don't care about the relations between the nodes?
We,
In both ways.
what do you mean?
Because there are like, you can have a connection from 1 to 2 and then 2 to 1. Like
Yes, I was going to say that. So networks can be directed or undirected. Directed is if there is if the edges, let's say, to put it in a way, have an arrow. If communication or material goes only from 1 to 2, and undirected otherwise. Okay? It is relevant and it makes a change, it makes a difference, but right now understand that we're just doing baby steps. Okay? Any questions so far?
I have a question.
Yeah.
When it's undirected, would we write the edges as 1, 2, and 2, 1, or like in that one?
If it's undirected, you would write, well, actually, here we should write like this. Okay. But I didn't want to go so much in detail. But now that you're asking.
In the case of the opposite, it's non-specified being goes both ways. You would put like the double-ended arrow.
No, you would put a comma if there is no arrow, just like I did before. Okay. So more questions? Anybody online has questions? So this is the example of a network. Which is a non-Euclidean data set. Let's see how we can measure networks. So, how can we quantify and compare networks? Okay, so we use 3 KPIs for that. The first one is it's called the average path length. Second one is called the clustering coefficient. Third one is called the Laplacian matrix. Sorry, the degree distribution. Laplacian matrix, something different. Degree distribution. Okay. So let's see what this means. And average path length is also called APL, CC, and DD. Okay, that's how I'll refer to them from now on. So the average path length is the average distance in steps between the nodes in the network. The formula, if you ask me, are some cheat sheet allowed in the exam? No. Okay, you cannot have a list of formulas in the exam. You need to know everything. Okay, no, nothing but a non-programmable computer.
Sorry, non-what? Non-programmable.
And non-programmable calculator. Okay. So 1 divided by n times n minus 1. I'll explain the formula in a minute. Just let me first write it down. The ij is the distance, the number of steps. The sum goes along all the steps, so all the relationships are taken into consideration. And why do we divide by 1 divided by n times n minus 1? Because the maximum number, well, we have an average, okay? It's an average. An average means that we need to divide whatever number by the maximum number of these relationships, just when you have the average number of something, okay? So the maximum number, of relationships in a network of n elements is n times n minus 1, because each element relates or can relate to all others, hence n minus 1 n times. I am a member, I relate to all of you, so we have n minus 1 relationships, and this repeats n times. That's why the maximum number in a network is n times n minus 1. Does this make sense?
Why is it divide 1 at the top?
It's divided by 1 because we need to have it here dividing, not up. We are calculating the average. But this is like this. It's the same, okay? So the other term represents the sum of all paths between nodes. Okay? That's why, hence, the average number of paths, the average path length. Let's see an example, and then it will be, I think, quite reasonable, quite easy. Let's take the network from before, non-directed. Okay, and let's calculate the average path length. Just stay with me, don't start writing or something, just look at the, hey, Saitia here, are you here with me or are you somewhere else? Yeah, are you sure? Because if you have something different to do, just go, okay? No problem. Let's look at the formula. N equals 6, okay? We have 6 nodes. N minus 1 is hence 5. And then I need to calculate all the distances between all the nodes. So now stay with me, okay? For node 1, what is the distance between node 1 and node 2 in number of steps? 1 step, okay? I only need 1 step. So the distance between 1 and 2 is 1. Plus distance between 1 and 3, 1. I only need 1 step, right? Distance between 1 and 4, 2 steps. I always take the shortest, okay? 2 steps. Distance between 1 and 5, 2. And then distance between 1 and 6, 1, 2, no, 1, 2, 3. Okay? Let me change this a bit to have the same example as above. I think we did this, but it's the same. So 1, 2, 3. Okay? Good. If I ask this question, calculate the average path length in the exam, this is just like giving you points like for free. Because you see, you just need to add 1, 2, and 3. If you make there a mistake, then I'm sorry for you. Okay? If it's wrong, it's wrong. Don't start, I have the concept or so. No. If it's 10 tracks, it's not 100 tracks, even if there is only 1 0 more. You understand me? So this is business. We do it right or we do it wrong. We don't do it so schwanger or nicht schwanger. Not in the middle. You're pregnant or not, but you're not half. So what is the distance between 2 and 1? Also 1. The distance between 2 and 3, sorry. 1. The distance between 2 and 4. 2. The distance between 2 and 5. 2 again. 2 and 6.
2.
Let's see. 1, 2, 3. Okay? Yeah, no problem. I mean, the first time it's okay, but then once the concept is understood, I think it's pretty easy. So for node number 3, distance between 3 and 1, 1. The distance between 3 and 2, 1. Distance between 3 and 4, 1. Distance between 3 and 5, also 1. Distance between 3 and 6, 2. So 2 because 3 and 6, okay? So number 4, distance between 4 and 1, 2. 4 and 2, 2. 4 and 3, 1. 4 and 5, 1. 4 and 6, 1. And between 5 and 1, 2. Here, 1, 2, okay? Plus 5 and 2, 2. 5 and 3, 1. 5 and 4, 1. 5 and 6, 2. And last, number 6, distance between 6 and 1, 3. 6 and 2, 3. 6 and 3, 2. 6 and 4, 1. 6 and 5, 2. Close the parentheses, do the math, and then you have a value. Okay? Whatever it is, I don't know. Somewhere between 2 and 3.
In that way you made a combination with each number, all the possibilities.
This is the sum of all paths between all nodes. Because I took the number 1 with all the rest, number 2 with all the rest, number 3 with all the rest, and so on. And divided by the maximum number of relationships. So this is why it's called the average path length. And this is a measure of how fast you get information. Habt ihr eine Frage? Was Lustiges? Oder?
Alles gut, alles gut.
No? This is a measure of how fast you get information or material or whatever from A to B in a network. Is this important? Well, if you have an informatics system and you want to get an email from A to B, it's important, right? If you have a logistics system and you want to get a parcel from Amazon to the customer, it's important to get there fast, right? So you don't want to have a lot of steps in between, you want to be there fast. The average path length is going to help us compare two processes. In 1 or 2 years, you're managers. And you have to buy two processes. One process works with an average path length of 100, the other process works with an average path length of 50. And this is just numbers, okay? You can do this with 3 lines of code. It helps you decide the second process is better, in theory, okay? Then you can go in detail and maybe say, no, but there's better quality, but they're going to be less complicated. They're going to be less, more value adding if the average path length is lower. Okay, so yeah.
And somebody can define like the point where which it fails, like when node 3 fails, the connection to point 1 and 2.
Yeah, that's the next. So this is going to be in 3 lectures. Okay, when this node fails, the whole network disappears.
Yeah.
So this node number 3 is crucial. Okay, it's a bottleneck.
And also we don't have to count for 1 and 2 because 1 and 2 like durations are all the same.
Yeah, well, yeah. Sometimes you need it for, but yeah, there are ways. Hey, wait a minute. There are ways to calculate these bottlenecks. We will see them. Just allow me for a little bit more. Okay, we're just starting. So, you have any questions?
No, I was just asking him one of the notes.
Okay. Yeah. So let's compare. So one of the questions that I could ask in the exam is, please compare. You can do that, okay? If you want to. Example. I will not because it's just, I think it's trivial. Compare following 2 graphs in terms of performance related to APL. Okay? So you have graph 1. And then you have, wait. Yeah, that's okay. And then you have graph 2. Okay, so you can calculate APL1, APL2, and tell me which graph would be more effective in terms of APL. Okay? So when you compare, you can do that yourselves. When you compare two networks, the one with the shortest APL would be usually faster or more effective. Okay? That's a fact. It's a physical fact, just like some people are taller and some are smaller, okay? It's just made out of the structure of the network. So this is serves as an introduction for the average path length. You understand how to calculate it. Last year I asked this question in the exam. So given a graph, calculate the average path length. Just giving points for free, I guess. Okay. Any questions? No questions? The second KPI that we look at is the clustering coefficient. So the clustering coefficient describes how good groups are created in the network basically it calculates the number of triangles that there are in the network and does something with that. The formula, I mean, when you have a group of people in one department, you want them to communicate effectively with each other, right? So you want to have a cluster that everyone knows what's going on and that the information goes and effectively. And then you have a cluster, you have a group, you have a cluster of friends and they know each other, they know more about each other than they know about somebody in the street, stuff like that, okay? So the clustering coefficient, the formula is 1 divided by n times the sum of to all nodes 2 times L sub I divided by k sub I minus 1. Okay, let me explain what these numbers mean. L sub I means, now please pay attention, the number of relationships between the neighbors of node I. So I am node I. The number of relationships, imagine I'm your friend and I'm your friend. And you're friends to each other. We have a relationship, so we are related, we are connected, and you are connected. So the number of relationships that my friends have to each other. How many of my friends are friends to each other? Okay? How many of my friends are friends to each other, to put it in a non-formal way, okay? K sub I means the number of friends I have, the number of neighbors of node I. Okay? So how many neighbors I have, how many nodes are my friends. So let's look at an example. you will see that the first time is not easy, but the second time you see it is quite straightforward. So please stay with me. Don't go, and then you'll get it pretty soon. So this is our network that we are using, same as above. So now the clustering coefficient is going to be 1 divided by 6. And I always do it the same, okay, so that I don't get lost, because I am very, otherwise I make mistakes. So for node number 1, please follow me, okay? So 2 is, yeah, wait, don't go so fast. I'll explain the first one. This 2 is this 2, okay? That's just no-brainer. So how many neighbors does node number 1 have?
2.
Which are 3 and 2, right?
Yeah.
How many relationships they have to each other? 1. Okay? So L sub 1 is 1. This is L sub 1. Node number 1 has 2 neighbors with 1 relationship. Okay? Divided by how many nodes are friends of node number 1? 2 times 2 minus 1. Okay? Plus 2 times, for node number 2, how many are the neighbors of node number 2? 2. They have 1 relationship. So 2 nodes, they have 1 relationship. And then again 2 minus 1 plus, for node number 3, it's a little bit more tricky. I have 1, 2, 3, and 4 neighbors. How many relationships they have to each other?
Just one question within that. So does the direction of the arrows affect?
No, forget about the arrows.
So then it would be 4 numbers.
Yeah, 4, but how many relationships do they have to each other? 2. This one and this one, okay? So this is 2 times 2 divided by 4. 4 minus 1. For node number 4, I have 3 neighbors.
Sorry.
Yeah.
I didn't get the thing that you said they had 2 relationships, because the number was 2. So would they have
Number 3 has 1, 2, 1, 2, 3, 4 neighbors. And these 4 neighbors have 2 relationships between each other. 1 to 2 and 5 to 4.
Let me see now.
No more. Okay? That's why this is a 2. Make sense?
No, it makes.
What?
No, it doesn't.
Yeah? Good. So for node number 4, I have 1, 2, and 3 neighbors. They have one relationship to each other. For node number 5, I have two neighbors, they have one relationship to each other. For node number 6, I have only one neighbor, and with one neighbor it's just nothing. Okay? So if you calculate this, which is again easy, you get the clustering coefficient of this network. Okay? Questions? Yeah.
And there's not a certain range of numbers which are usual, like in like the correlation between the probability between 0 and 1. It depends on the size of the network and all this. So the number can of the correlation coefficient. You know, I mean this. It can be any number.
It is not. It is not a. No, sorry. It's not a correlation coefficient. It's a clustering coefficient.
No. I just mean, is there? It can be any number. The result can be any number, or is there?
No. It has to do with the size of the node. Yeah, of course. It has to do with the n. It depends on n. Yeah. That's why we can only use it to compare networks that have the same size or similar size. But still, we are only making baby steps still. Okay, so please allow for some time. The higher the clustering coefficient, the better the communication between the elements of the network. Okay? So if you go and you can say, let's compare these two graphs in terms of clustering coefficient. G1, 1, 2, 3, 3, 4, 4, 5, 6, 3, 6, okay, and G2, 1, 3, 2, 1, 6, I don't know, just 2, 4, 3, 6, 3, 5, okay, so how would you do that? The same way as we did before, okay? So feel free to practice, because this could be, it was one of the questions in the exam last semester, I guess. Any questions on how this is calculated? Yeah.
Just a comment. It can't be any number. It can be just a positive number between 0 and 1. Like just except if we can say they have like a negative relationship. Like
No, it can be any positive number. It will not be negative.
okay. Even if you take like yeah.
It will not be negative. Okay. So, any questions so far? Those of you online, please make a sign that you're still there. You have questions? Was steht da? Ich kann es nicht lesen. Was steht da?
Will n always be 6, or do you also use 2-digit as n?
So I don't understand your question. Can you please make your put your microphone on and ask the question? Hello? Isha, so the guy is asking if n can be greater than 6. It can be, of course, it can be infinite. If you mean in the exam, I am not going to answer the question. Okay? So nice try. Yeah, sorry. I don't answer questions about the exam, as you can imagine. Okay? Otherwise, what's the point of making an exam? All right, good. Then let's. Next concept is the Laplacian of a network. I guess I'm going to explain the Laplacian of a network and not the degree, because this is more general. Let me change it here in the list that I made in the beginning. The Laplacian of a network. And this is a method to transform a network into something that can be Euclidean. So the Laplacian matrix of a network describes, contains all relevant information of a network. Okay, is defined as L equal D minus A where L is the Laplacian matrix D is the degree distribution matrix and A is the adjacency matrix. Okay? So let's see what this means. You will see it's easy, okay? It's just very intuitive, but you need to follow me, okay? So the degree matrix, this is just a little bit of math, okay? Don't get bogged by it. It has in the diagonal, if I equals j, the distance between the two nodes, and 0 otherwise. Okay? So dij is the degree of the node, what we called before k sub I. I guess I can use the same nomenclature as before, so k sub I, degree of node. And A is the adjacency matrix. And it has this probability. It has a 1 if A, I, and J have a connection. And a 0 otherwise. Okay? Let's make an example and you will see it's super easy. So there will be no problem for you to understand this. So I copy the same network as before. Now it's relevant that you look at the directions. So now let's see how we create the Laplacian matrix. And this is important because this helps us do a lot of things with the network. So the Laplacian of the matrix is created like this. Let's say it has 5 and 6. This is going to be the degree matrix. 1, 2, 3, 4, 5, and 6. So it said there it has k sub I in the diagonal and 0 in the rest. Good. Then what is the degree of node number 1? I always do this. Okay, please look. I always do this. How many crosses do I have? 2. Okay? So I have 2. Around node number 2, I also have 2 crosses, right? Around node number 3, I have 4 crosses. Around node number 4, I have 3 crosses. Node number 5, I have 2. Node number 6, I have 1. Okay? Make sense? The rest is a big 0. So you can put it like that. Big 0 there. Minus. Here we do the same. 1, 2, 3, 4, 5, and 6. Of course, you can do it also without this help of the little numbers, but I do it because it helps me not get lost. So 1 with 1 has no relation. So it has this has a 1 if A and J have a connection and 0 otherwise. So here we have a 0 because 1 doesn't have a connection with 1. We have a 1 because 1 has a connection to 2. We have a 1 because 1 has a connection to 3. We have no connection between 1 and 4, 1 and 5, or 1 and 6. Okay? Number 1 has a connection to 2. No, No, number 2 has a connection, okay? So here is a 0 because there is no arrow like this. It's your question from before, okay? So here's a 0, here's again a 0. 2 does not have a connection to 2. 2 has a connection to 3, yes. Not to 4, not to 5, no, not to 6. Okay? Can you follow so far? Number 3 has a connection to 1, no. Connection to 2, no. Connection to 3, no. Connection to 4, yes. Connection to 5, yes. Connection to 6, no. Number 4 has a connection to 1, no. To 2, no. To 3, no. To 5, yes. To 4, no. To 5, yes. To 6, yes. Number 5 has 0. It's an end node, and number 6 has 0. It's also an end node. Okay? So now we're cool. We can make our Laplacian matrix pretty easily. This is A. Okay? So our Laplacian matrix looks like this. Two. So this is 1, 2, 3, 4, 5, and 6. And this is 1, 2. 1, 2, 3, 4, 5. And 6. Okay, so for node number 1, well, this is straightforward. We have a 2 in the diagonal, which comes from here, okay? And then minus 1, 1, minus 1, 0, 0, 0. So whatever it was a 1 here, because I have a minus before, turns into minus 1. Okay? I mean, not really super difficult. So here again, 0, 2, minus 1, and then the rest zeros. I'm here. Okay? The third one, 0, 0, 0, no, 0, 0, 4, minus 1, 0. The next one, 0, 0, 0, 3, minus 1. And then I have a 2 and a 1, and the rest are zeros. All right. Yeah.
I have a question. How to calculate it when there is a connection between 6 to 1? You would also calculate it like 1 minus.
If there is what a connection from 6 to 1,
Yeah.
then I would have here a 1.
That it will be 1 minus. Yeah, okay, this is a bad example.
And then I would have here,
Connection to 6 to 2.
and then I would have here a minus 1. This would be it.
A minus, okay.
What is bothering you?
Because
If I have a connection where?
from 6 to 1 and maybe 6 to 2, and then there are 2 1s on the one side, on the left side, and
No. If there would be a connection between 6 to 2, like this, then your matrix would be here at 2. Okay?
Mhm.
And then your matrix would be here, would be having here a 3. And then you would be having here a 1. Okay?
And at the bottom it would be 2 minus
What was that?
minus 1. At the bottom,
Yeah, it would be minus 1. Yeah.
okay, yeah.
Okay?
Mhm.
All right.
Just looking to got it correctly. The first block, you're talking about the connections, no matter what direction they go, the arrows. On the second, it would be the question of the one leaving from the number.
Yes. Yeah, the one is the degree, the other one is the adjacency. Okay? So once you have this is important because in the beginning we had a network which is a graph with nodes and edges. And now we have a Laplacian matrix with exactly the same information. The network is non-Euclidean. The Laplacian matrix is Euclidean. And this is a huge difference. Because now we can do things to this matrix and calculate things to this with this matrix and get information that is relevant for us, for instance, bottlenecks, for instance, a couple things. And this is relevant for our next steps in the future. Okay? So we have transformed a non-Euclidean data set into an Euclidean data set. And now we can do other things that are relevant. Okay? That's why the Laplacian matrix is so important. Because, as I repeat, it has all relevant information of the matrix. So the first consequence of this is that the eigenvalues or better said eigenvectors of the Laplacian matrix contain the spectral, so-called spectral information of the network. Okay? So you need to recall how to calculate the eigenvalues of a matrix and the eigenvectors of a matrix. If you have a matrix A times the eigenvectors, this is also like this, okay? Where V is the eigenvectors and lambda is the eigenvalues. In order to calculate the eigenvalues, you need to do this determinant, lambda E equals 0. So therefore you get lambda, and with lambda you can get the eigenvectors, okay? So this is something that you should recall. If you don't know it, or you forgot already, make sure you look it up, because it's important, okay? The second eigenvector of the Laplacian matrix of the graph is called the Fiedler vector. And the Fiedler vector, Fiedler by the guy who discovered it, the Fiedler vector has an important property. It has a sign structure that shows the bottleneck of the graph. How it does it? Imagine you have a graph with nodes and edges. You have the Laplacian matrix. You calculate the Fiedler vector. The second eigenvector of the graph, of the Laplacian matrix of the graph. And it has this characteristic. If you order the nodes 1, 2, 3, to I don't know, n. The nodes are ordered like this. At some point you will find some zeros, and if you continue, at some point you will find some minus values. The first node in which you find the 0 is the bottleneck of the So the first 0 that you find is the bottleneck of your graph. If you would do this exercise with this graph, you will notice that the first 0 you find at node number 3. Because if this node dies, you don't have a network anymore. You have 2 networks. Okay? Make sense?
Which 0 is it? Because there's a 0 at 1, 2. Because
Noma?
you said the first 0 is at node 3, but I don't, because there is also a 0 in the line with the 1.
No, it doesn't have to do with the matrix here. I'm talking about the eigenvalues and eigenvectors. This is something different.
Okay.
This is the eigenvector.
Okay.
You know what I mean with eigenvector, or no?
No.
Please look at it in your algebra books from the first semester, okay? Because you have seen it. It's super important for Wirtschaftsingenieur. If you don't find it, let me know next week, okay? All right. So, any questions? But please really look it up, okay? So, because it's important. It's Otherwise, I wouldn't be saying it. Okay, so you need to understand what is the eigenvector of a matrix. So if you guys want to try yourselves, okay, this is not a must, but you can do it, and I will gladly correct it. I give you an exercise. Please write a Python code 3.x that generates two graphs each with 100 nodes, and each node attached to a vector of 300 elements. Can be a random vector, okay? It doesn't need to. That is normally distributed with normal degree of the node and standard deviation the square root of the degree of the node. This is for the first graph, network 1, and network 2, degree of the node square as mean value, and cubic of the degree of the node for network 2. So the first one is the mean value, the second one is the standard deviation. The code should then calculate the Fiedler vector of each graph and you should interpret the results. The networks should have a so-called Barabasi structure with gamma or exponent degree 2.4. So all this is, you don't have to know it, okay? It's not compulsory. You can do it or not. You can ask GPT to do it for you and see what happens. I just would like you to, I would like to challenge you to solve this problem and be able to interpret both the code and the results, okay? Basically, this problem is a general problem in the industry because what you find in the industry is just not only a network, but a network in which the nodes and the edges are creating data. Okay? All the time. If you have your Amazon carrier, the truck of Amazon is sending data to the cloud. When you scan the packet, it's sending data to the cloud. All the time, data are being generated in the network, and this has an influence in the decisions that you make all the time. So basically what you have is a network which is a non-Euclidean data set and the nodes and the edges of the network are generating data in time. The nodes and the edges are generating data in time all the time. And this has an influence on the performance, has an influence on the decisions that you make in order to get your network to perform. Okay? So this is a general problem, and I would like you to try to model it into Python, if you want to. Okay? So. Okay, any questions? All right. So then we have a network topology aspect as well. That we are going to be tackling today as well, and this starts like this. So this is our last topic today. The probability that a node with k neighbors attaches a new node in a random network is given by a Poisson distribution. Remember your statistic class with parameter lambda, which is the rate. So the probability that the node with k degree, yeah, question? That the node with k degree attaches a new node. That's what p sub k means. You can also write it like this. Sorry. It's given by a Poisson distribution, which has typically this formula. Okay. So this is for a random network. You pick somebody random, or you pick some friend random in Facebook. No attachment, just click and say, I'm going to follow you, stuff like that. So in real networks, the behavior is different. The probability that a node is connected to another with k neighbors in real networks is given by what we called a power law distribution. Okay, which is this is all statistics. It's given by k to the potent of gamma, being gamma the exponent degree. In the exercise above, remember I talked about a Barabasi structure with exponent degree 2.4. The Barabasi structure is a real network. It's a model for modeling real networks. Okay. So the random networks are Poisson distributed. Which means we can use all the statistic tools that allow us for calculating the characteristics of this distribution, and then we have the exponent degree power law based and for real networks. Okay, so behavior is different. And let me just explain a little bit what this means for you. Okay, so I will digest a little bit. A recommendation that I make, if you want to, you don't have to, but if you want to learn more about networks, which I recommend, of course, is one book called Network Science. The author is called Barabasi. This is like the priest, the papst of the network science. One guy from Hungary does research in the US. This is a super duper good book. Okay, it's pretty tough on the math, but I totally recommend that you buy it and study it hard, because it will help you understand a lot of things in business. Okay. Anyway, so how do we represent this graphically, and what are the interpretations of the graph? Let's look at it. So if this is the logarithm of the degree, and this is the logarithm of the probability, we fix the gamma to 2.1. Real networks behave like this. Okay, this is around for gamma 2.1, but the values that we get. So real networks go in a slope, constant slope, in a log-log representation. And random networks, because they are represented by a Poisson distribution, they go like a little bit like this. trembling hands. So this would be 10 to the point of 2, and then this would be 10 to minus 3, something like that, okay? So what does this mean? There's a peak here around 10. This is the random network. And this is about the average, this is the average degree. It means that there are 2 points here that are crucial. Sorry. One there and one there. On the left of the first point, the real network is bigger. On the right of the second point, so here, the real network beats the random network is higher. Here, the real network beats the random network. In between, the random network is higher. Okay, so the real curve is a little bit like this. Okay? So this can help us define 3 phases, 3 parts of our business. Yeah.
What are the x's again?
The logarithm of the degree here, and the logarithm of the probability here. Okay? The probability that you communicate, imagine you are in Facebook, what is the probability that you communicate with her?
High, like most.
Why? Because
She and me, we know me.
you're in the same class, maybe. What is the probability that you connect with her cousin, I don't know, who lives in San Francisco?
A bit less.
Less. What is the probability that you connect with some random person who lives in Nigeria?
Really low.
Really low. So it depends if it's a random process or it's a real thing. Okay? The probability of connecting is different. I don't know. Okay? It's different. And this is what we are modeling here. We have, as I said, 3 phases, 3 areas. Area number 1, number 2, number 3. Okay? Let's look at them in detail. This I asked last year in the exam as also. Okay? I don't know, somebody wrote the exam? No? No? Yeah, this was asked. In the area number 1, what do we have? Random is way smaller than real. So for small degrees, small networks, networks in which people don't have a lot of friends, small degree, okay? The power law of the real network is above the Poisson random network, indicating that the real world has more nodes with few neighbors than a random process. Okay. So in the real world, there are more nodes with few neighbors than there is in a random process. Area number 2. Here, things are different. The random is bigger than the real. For nodes around the average degree, the mean value of the degree, the random network has excess of nodes. This is why cookies can damage IT systems, because they are random, they go everywhere, and they have an excess of nodes with those degrees. Okay? We have more nodes with more nodes with an average degree in the random network than in the real network. This is also a way to find out if a network is real or not. Okay? Or it's made out of synthetic data. It's a way to find out if somebody is cheating or using ChatGPT or not in a bachelor Arbeit. Okay? Because you can translate the text into a network, and then you see if the network is synthetic or not. Okay? And so random, the third area is to see if random is smaller than real. So for large degrees, the real network presents more nodes with high K, with high degree. They are called how? Influencers. They're hubs. They're people with a lot of friends. Okay? This is the sweet spot. This is where you earn money if you are into networks. Okay? So you want to move there. In order to do that, you need to know the dynamics of the network. You need to know how to trigger a network and so on. Okay? How to manipulate the elements of the network. So this is important, okay? Just this little graphic is important to understand. Any questions?
Do we have to calculate something there, or
No.
only understanding?
Yeah.
Okay.
I didn't calculate anything here, right?
Yeah, no, because of the in the box. I thought maybe
Well, you need this you need to know.
Yeah, but we don't have to put numbers inside.
I don't know, maybe. But not now.
Okay.
Maybe later. You ask me like with some fear expression, like something like like a lamb going to be killed by some chopper. No, I don't know. Please try to understand this, okay? And try to deep dive a little bit. You can go into Google and maybe Google what is a Barabasi network. You can be a little bit curious about examples on the Barabasi. You can ask your GPT for something useful, like give me some examples and why is random network different than a real network, and so on. So what I'm trying to do is I'm trying to teach you how to fish. I'm not giving you fishes, okay? That's my point here. You're in the 6th semester already, so you should be having already a degree of maturity that allows you to look around and see what it's interesting for you, I guess. That's my idea of teaching, not showing how smart I can be. Because if I start deep diving into the theory of the mathematical theory behind all this, then I tell you something and I'm alone, you fall asleep or you go. I don't have any interest on that. Okay? I want you to find this interesting because I am sure this can help you get more money when you go out there and find a job. So if your goal is to have a better life, study this in detail, because this can help you get more money for real. This is really the life that you are going to live out there. Networks are everywhere, in the social level, in the technical level, they're in the business level, they are every fucking where. So if you understand them better than others, you have an advantage. Yeah.
Is there a certificate for networking or like the network systems?
What?
Is there like a specific certificate, for example, there's a certificate for project management or certificates for something?
No, I don't know. If you learn this book and you understand it, then you can call yourself certified network expert. But no, I don't know. There are some masters that go into network science in detail. I know one in Madrid, but just because I come from there. In the US, but I don't know. Maybe there are some certificates. I'm not really a certificate guy, so. So let's look at the role of the exponent gamma. If gamma is smaller than 2 or equal to 2, we have an anomalous regime, and I will not get into the detail here. Networks cannot exist long. This is what happens when cancer kills a body. Cancer brings the body cells to gamma smaller than 2, and then the body cells stop working as a network, the body dies. Okay? This explains this process. If gamma is between 2 and 3, networks grow. This is the scale-free regime. So networks grow healthy, so they can exist, they can grow. If gamma is bigger than 3, then we have a random regime. And see above, okay? So we either have a real regime in which between 2 and 3, or we have a random regime, or we have a smaller than 2 regime in which we die. Okay? The network just breaks down. It has more degrees, more nodes than degrees, and this is impossible. Okay.